This is an introduction to truth functional connectives and a little bit on the truth table method. First, consider this argument. Not both Percy and Quincy will be at the zoo. Another way to say that is Percy and Quincy will not both be at the zoo. Quincy will be at the zoo, therefore Percy will not be at the zoo. We can check for the validity of that argument by trying to give a scenario, or an interpretation we could call it, that makes the premises true and the conclusion false. First, make the conclusion false. Since the conclusion says Percy will not be at the zoo, to make it false, we need Percy to be at the zoo. Now let's make the second premise true also. Quincy will be at the zoo. We have to put Quincy there too. Now make the first premise true. By the way, we don't have to go through in this reverse order. It just makes sense for this problem and what I'm trying to show to go through it from bottom to top. Now let's try and make the first premise true. Not both Percy and Quincy will be at the zoo. Uh-oh. Making the first premise true, that Percy and Quincy are not both at the zoo, makes the conclusion true if Percy's not at the zoo. Or it makes the second premise true if Quincy's not at the zoo. Making the second premise true, in other words, and the conclusion false, required that the first premise be false. Because we can't make the conclusion false if the premises are true, it looks like the argument is valid. But did we give up too soon? Maybe we didn't think of enough scenarios. We only tried the one. No, we didn't give up too soon. Let's think about it some more. Here's the argument again. Let Q stand for the sentence, Quincy will be at the zoo. Notice Q doesn't stand for Quincy. That's why I picked the letter Q. But the letter Q stands for the whole sentence. If I wanted a letter to stand for an individual thing, then it would be a lowercase letter. I'd call it a constant. If you're familiar with the more complex notation, then we could say Q, capital Q, by saying zoo Q. If zoo means will be at the zoo, as the predicate will be at the zoo, and Q is a constant that stands for Quincy, then this sentence would say Quincy has the characteristic of will be at the zoo. If that notation is not familiar to you, ignore it. Now, if we let P stand for Percy will be at the zoo, then the conclusion could be represented by not P. With those abbreviations, the first premise is not both P and Q. Not both P and Q technically says it's not true that both Percy's at the zoo and Quincy's at the zoo. But notice that mouthful is just another way of saying premise 1. So here's our abbreviated argument. Not both P and Q, Q, so not P. To check for formal validity, we could try and plug in sentences for P and Q, and in doing that, give the argument all true premises and a false conclusion. But there's a shortcut that shows that no matter how hard we try at that, we'll never be able to do it. If the conclusion is going to be false, then sentence P, whatever it is, has to be true, because the conclusion says it's not true. So, if we plug in a true sentence for P and the conclusion says it's not true, then we'll end up saying something false. Now, if the second premise is true, then Q is true. But P is true, and also Q is true. So that means P and Q is true. We know that because we know how the word and works. Now the first premise, which says not both P and Q, must be false. Because remember, both P and Q was true. So to say it's not is false. So no matter how hard we think about a scenario or about new sentences to substitute for P and Q, we'll never be able to make the premises true and the conclusion false. Making the second premise true and the conclusion false required that the first premise be false. We'll never get true premises and a false conclusion. That means the argument is valid, or in other words, the premises logically entail the conclusion. We can be sure of that this time. It's tough to be certain of validity when you're thinking of counterexamples. remember our uncertainty before, maybe we didn't think of enough scenarios. We can be sure in this case because of the way and not work. We know this about and. If P is true and Q is true, then P and Q is also true. And we know this about not. If a sentence X is true, then the sentence not X is false. And not are truth functional connectives. Here's what that means. They can be used to combine with other sentences to make new sentences. And the truth of those new sentences, or the falsity of those new sentences, is completely determined by the truth of the smaller sentences that combine to make the new sentence. All I have to know whether P and Q is true is whether P is true and Q is true. Not as symbolized with those two symbols. The function those symbols represent is called negation. We know that if P is true, then not P is false, and if P is false, then not P is true. Here's a table representing that same information. If P is the input value, then not P flips to false. If false is the input value for P, that is, if sentence P is false, then saying not P is true. Of course, we can communicate all the same information with the other symbol, the tilde. And is symbolized with a dot, or an ampersand, or a caret. The function represented by those symbols, all of them are interchangeable, is called conjunction. Let's start directly with the chart this time. If sentence P is true and sentence Q is true, what is it to say that P and Q? Well, that's true. Think about Percy and Quincy. If it's true that Percy's at the zoo, and it's true that Quincy's at the zoo, then it's true that Percy and Quincy are there. Let's consider the next possibility. Think of each row on this table as a possibility. This is the possibility where it's true that Percy's at the zoo, and it's false that Quincy's at the zoo. So to say they're both there then is false. The next row is similar. If Percy's not there and Quincy is there, then to say Percy and Quincy are there is false. Now, if neither one of them are there, if it's false that Percy's there and false that Quincy's there, then it's sure false that they're both there. Now, I went through that using the Percy and Quincy example, but I didn't have to be. We could plug in any two sentences for P and Q, and the result would be the same. That's what it means to say that the caret, or the function conjunction, is truth functional. There's no way of plugging in two true sentences and getting anything but a true sentence out. Similarly for the other rows, there's no way of plugging in a false sentence for P, whatever it is, and a true sentence for Q, whatever it is, and getting anything but a false sentence out. I could communicate all that same information with the other symbols, with a dot here, or an ampersand. The symbols are interchangeable. The sentence not both P and Q could be represented this way. Not both of them. P caret Q, this line right here, says both P and Q. Not P caret Q says both not P and Q. Look at this for a second. This negation just applies to this P in this notation. So this says not P is true, and also Q is true. If we're trying to say not both, this doesn't say it. This says both not P and Q are true. That's not what we were trying to say. We were trying to say it's not true that both of them. That's what the bottom line says. It's not true that both of them. Of course, we could communicate all that same information with the dot or the ampersand. Don't be confused by different symbols. Let's try and fill out a table for not both P and Q. This should be familiar to you. I just used the table that we had before for P and Q. Now let's calculate the value of this larger sentence. If P and Q is true in this possibility, then saying it's not true is false. If P and Q is false on this possibility, where P is true and Q is false, then saying it's not the case that this sentence must be true. The next row flips false to true, and the final row flips false to true. Now, we could do this mechanically just by taking the t and flipping it to f, because that's how negation works, or we could think our way through it each time. Remember the full argument? Let's try and put that on the table. I added the other premises here. Remember, the second premise of our argument was Quincy will be at the zoo, and the conclusion was Percy will not be at the zoo. The second premise of this argument is just Q. And over here, where we were keeping track of the possible values for Q, we had that Q could be true or false, depending on P. So I just copied that column over here, true, false, true, false. Now the conclusion of our argument was that Percy will not be at the zoo, or not P. If the value of P is true, then the value of not P is false. That's how negation works. If the value of P is false, then the value of not P is true. So this column over here is the flip of the P column. Now here's the interesting thing. We've represented all the possibilities that matter for this argument. The truth values of the premises in the conclusion are completely determined by the truth values of the components. There are only these components, and there are only these possible combinations of values for the components. There are just 4. When we worried before that we hadn't considered all the possibilities, what we've done here is narrow the possibilities to 4 that need to be considered, and we can tell at a glance that we've considered them all. The first one is P and Q both true. That scenario makes the first premise false, the second premise true, and the conclusion false. That's not a scenario that gives this argument true premises and a false conclusion. That's just one scenario. Here's the next one. If P is true and Q is false, then this argument has a true premise, a false premise, and a false conclusion. If P is false and Q is true, then this argument has all true premises and a true conclusion. That row on its own looks nice because everything is true, but it doesn't tell us anything more than this. This argument could have true premises and a true conclusion. What's important for validity is that it can't have true premises and a false conclusion. And the next row shows us that here's another one that doesn't have true premises and a false conclusion. In fact, none of the rows have true premises and a false conclusion. That means none of the 4 possibilities that matter for this argument make it invalid or show that it could have true premises and a false conclusion, so the argument is valid. We'll do more on truth tables. I just included this one to convince you that it's a very powerful method. In order to use it successfully, we'll have to back up and talk about other truth functions. We'll do that next.